Hi everyone. Thanks, Yamila, for the introduction, and thanks for the opportunity to share some of what I've been working on recently. This is very much a work in progress, and in fact, Steve and I were up late last night doing some of these observations, so this will also be kind of an experiment and giving a talk at 6 a.m. after observing the night before. So let's get into it. And I'm sorry that my cat is trying to get into the cupboard behind me. Let me move her real quick. Sorry. So most exoplanet imaging efforts have focused on imaging young giant exoplanets that radiate most of their thermal emission in the near IR. And if we want to image thermal emission from more temperate planets like the Earth, then we need to go to longer wavelengths. So by examining a series of spectral energy distributions of decreasing temperature, the optimal wavelength range of about 10 microns becomes apparent for detecting habitable zone planets similar to Earth in temperature. And in order to image this thermal emission, the techniques of exoplanet imaging that were traditionally developed in the near infrared will need to be extended to the mid infrared. And the primary limitation here that's already been pointed out in the previous talks, and which is rather obvious, is that the Earth's atmosphere, the telescope, and the detector are all glowing at us at these wavelengths. And of course, by going to longer wavelengths, we're also dealing with a larger instrumental PSF and a wider inner working angle. Here's an example of illustrating some of these challenges. So these images show the same planetary system imaged a bit further into the mid-infrared than the movie on the previous slide, at 4 microns in the middle and 5 microns on the right, with the NERC2 instrument on Keck. These observations were taken with the same instrument under similar conditions and for approximately equal amounts of exposure time. And the differences are really just in the wavelength. And you can see this as a higher thermal background that's present everywhere throughout the image on the right, and also as a more extended inner speckle pattern as the diffraction pattern scales with wavelength. And planet E is lost among this combined, or these two combined sources of noise. And you can imagine that these issues are even more pronounced if we were to double the wavelength again to 10 microns. Now, let's take a moment to consider what might be possible if we're able to achieve a similar level of performance at 10 microns as we can in the near infrared. The plot on the left shows the contrast ratios of hypothetical Earth analog planets around nearby stars. These planets are Earth analogs in the sense that they have equivalent radii, an Earth-like atmosphere, and receive an equivalent amount of stellar irradiation. Among this sample, hypothetical Earths around 2 stars, Alpha Cent A and B, lie within the range of sensitivity that's currently been achieved with extreme AO systems, actually now more than about half a decade ago. Notably, their habitable zones and those of a few other bright nearby stars are at separations of about an arcsecond, which are resolvable with current telescopes. The image on the right is from Hubble, operating in the optical, but the VLT operating at 10 microns has about the same angular resolution, and the habitable zones are shown in the shaded regions here. So beyond large aperture telescopes, there are a few key pieces of technology that make exoplanet imaging possible in the mid-infrared. The first that I want to tell you about is an adaptive or deformable secondary mirror. And this, in my opinion, is a pretty remarkable piece of equipment. The glass shell is sitting on a bed of neodymium rare earth magnets that both hold the mirror in place and also act as magnetic actuators to control the mirror's shape. This enables us to perform an adaptive optics correction at the secondary stage and to eliminate what would be additional warm optical elements in the system that would contribute to the overall thermal background. Another important piece of hardware is a 10 micron optimized coronagraph, or in this case, an annular groove phase mask, or AGPN. This is the sub-wavelength grating that acts like a pair of polarized sunglasses in which the polarization vector performs a complete 360-degree turn around the central axis. So this creates an effective central null, which occults the light from the central star while allowing the light from off-axis sources to pass through. And AGPMs have been widely used in the near infrared for exoplanet imaging and high contrast imaging in general. And the transition to longer wavelengths is actually kind of straightforward as the etching pattern also scales with the wavelength. And so does the precision that we need to achieve. So the final component that I want to tell you about that makes MidIR exoplanet imaging even possible with current detectors is the observing strategy. So in order to enable measuring and subtracting the relatively high background from the image, much of which is actually systematic noise from the detector, we perform rapid chopping at about 10 hertz, in which we alternate the position of the star on and off of the coronagraph in this image. By subtracting one image from the other, resulting with the subtraction pair on the right, most of the systematic features, in particular the excess low frequency noise from the detector, cancels out, resulting in essentially background limited performance and enables imaging planets of very low masses with sufficiently long exposures. So this brings us to the NEAR experiment, which stands for the relatively ambitious title of New Earths in the Alpha Centauri region. The goal of NEAR was to test out a full MidIR exoplanet imaging system to perform a long stare on the closest stars in order to provide a sort of proof of concept that the ELTs will be able to reach exo-Earth imaging sensitivities. NEAR was rather unique in that it was sponsored by both the Private Sector Breakthrough Foundation as well as ESO, and more than 40 people contributed their time and expertise into making the project a success. And I'm happy to see several of these people also here at this conference. The experiment was completed in 2019 and the results were published last year in Nature Communications. This slide shows the final combined image from the NEAR campaign on Alpha Centauri with two different simulated Saturn-sized planets in order to give you an idea of what a true source would look like in the data. And these simulated planets also give us a means to assess the sensitivity. And there is one possible candidate in the image labeled as C1, but ultimately this source requires further verification. I can say that we're confident this isn't a random false positive because it appears in multiple independent segments of the data, but we can't presently determine whether the source is a true positive, such as a planet or exo-Zodi disk, or whether it might just be a new and not yet well understood instrumental artifact. So here are the sensitivity limits from NEAR, which I think are really motivating for work going forward. So for Alpha Cent A on the left, we would be sensitive to warm Neptune-sized planets or cold Saturn-sized planets in the habitable zone. Whereas for Alpha Cent B, we would be sensitive to warm Saturn or Jupiter-sized planets in the habitable zone. These limits represent approximately an order of magnitude improvement in sensitivity, both in terms of mass and angular separation compared to typical exoplanet imaging observations, owing to the fact that we're detecting colder planets at longer wavelengths and also that we're observing the closest stars. So we get very good physical separation limits. And these results also support that the ELTs should be able to efficiently image Earth-sized planets around Alpha Centauri if those planets are out there. So building on this work, I've been leading a large program on the LBT focused on translating many of the lessons of NEAR and also on developing some new strategies in order to perform MidIR exoplanet imaging. The acronym for our program is called LESSONS, which is only slightly less ambitious than the NEAR acronym. We're focused on super Earths and sub Neptunes, going for a bit shorter exposure times, but imaging a larger volume of targets. With the LBT's dual 8.4 meter mirrors and a few other upgrades that we have planned, we expect to be able to push down to sensitivities that are ultimately about 2.5 times deeper than NEAR. And some of this is actually just owing to the site that the LBT is on, which is a high altitude inland peak opposed to a warmer site that's right next to the Pacific Ocean. So this slide shows some of our initial progress implementing chopping. And by ramping up chopping from 0.4 hertz to about 2.5 hertz, we notice an exponential decrease in noise, similar to what we found with NEAR. However, pushing to faster rates of chopping doesn't appear to give us any benefit. Our optimal chopping rate appears to be a bit slower, which actually makes the observations a bit easier. But if we could figure out why our noise is increasing here, we might be able to push a bit deeper even.
Kevin, you have 2 minutes.
Thank you. This is an image of Sirius, illustrating both that the system is working and that we're identifying some of the same systematic artifacts that we discovered with NEAR, such as the accumulated persistence during chopping. One component that we have yet to implement with LBTI is a MidIR optimized coronagraph. And we have some designs for what that would look like. And we've submitted a proposal to NSF's Advanced Technologies and Instrumentation call, and we're waiting to hear back. Our preferred design consists of 4 quadrants, each with a central null location, so that we can make full use of the double apertures and also of 100% of the observing time while still chopping in order to mitigate the background noise. And finally, I just want to leave you with an important scaling relation to think about, that the time required to reach a particular signal to noise scales as the -4th power of the diameter of the primary mirror. So that means that the upcoming ELTs will be able to complete in just minutes what currently takes hours with the BLT and LBT. So what currently would be a 100-hour long observation will soon be able to be completed in a single night. And several studies have confirmed what I think are the exciting predictions that the ELT should be capable of imaging exo-Earths within the nearest systems like Alpha Centauri. So I'll just leave you with my conclusions, and I'd be happy to take any questions. Thanks.
Great. Thanks for the nice talk. There are a few questions. One by Leo. He's asking, interesting plot showing the sensitivity versus chopping frequency. Have you been able to decompose the noise into sky and detector components too?
It's a very good question. And actually, I'll take that as a suggestion because we haven't tried that yet.
And then there is a comment, not really a question, also on the chopping frequency, saying that Chris Bachman is saying it looks very similar to the plot they found for both T-Rex, Gemini S, and Canary Cam, GTC.
Okay, I'd be interested to continue a discussion along these lines to see if we also see a similar blue noise component.
Okay, Bernhard is asking, now that we will soon have the technology to see planets around Alpha Centauri, what are the chances that there is none?
It's a very good chance that there's none. So of course, it's the binary system, and the closest separation, if I'm remembering correctly, early in the morning is around 8 AU or 10 AU or so. So this limits the range in which a stable planetary system could exist to about 3 AU. Luckily, that still includes the habitable zone. But from planet formation statistics, we don't expect there to be a higher than, I believe, in the tens of percent, but not high tens of percent, that there are detectable planets around Alpha Centauri.